Okay, well, here in a second. First, we need to talk about measuring concentration of acids and bases in real life, like in the laboratory. And one of the ways that we do it is with various types of pH indicators, okay? And one of them is what's called litmus paper or pH paper, okay? Litmus paper only has sort of an on-off thing. It's either red or it's blue. And the easiest way to remember whether a litmus paper is what it's telling you is that B for base, B for base, blue for base, okay? So if litmus paper turns blue, the solution is basic. If it stays red or turns more red, it's acidic. Now pH paper has a variety of different compounds that change different colors. And you'll see right down here there's like a pH scale depending on the color that it is that your paper turns. Okay, so it's a little more sophisticated. The other way that we do things is with pH indicators. Okay, and a very common one that we use in laboratory all the time, and is phenolphthalein, okay, which looks like it has far too many consonants for its own good. But phenolphthalein, okay, is colorless in acid. Okay, so our test tube on the left here is colorless, so that's going to be some kind of acidic solution, right? But once the solution turns basic, or if you're dealing with a basic solution to start with, the indicator will be pink. The next way that we do things quite often in laboratories is with pH meters. Okay, and the pH meter uses a probe to measure the pH in combination with a voltmeter. Basically, that digital box there is a fancy voltmeter. Okay, and it converts electrical signals from the pH meter into calculations that give us pH. Okay? And that's really the best way to go about things, but that's not a cheap instrument. All right, so this is what I was starting to talk about. So acid-base titrations, okay? And I'm going to very seriously cross out the dilution equation, okay? Because I don't want you to use it, okay? Don't use dilution equation for titrations. Because it will only complicate your life. Okay? I'm going to show you, we're going to deal with one way. So anytime you see a titration question, you have one method. It's easy and you've already done it. You already know how to do it. I don't want you to even have it in your mind that the dilution equation is an option, because it only works with 1-to-1 ratios, and you won't always have 1-to-1 ratios. So the best way is to go with one way to do things so that it applies to every single titration question. Okay? So what is a titration? Basically what you will have is, to start with, you'll have acid to start. Okay? And up here, in this device, you'll have some base. Okay? And you will very carefully, and then also in the beaker, I forgot you'll have an indicator, like phenolphthalein. Okay? So at first, your solution will be colorless because it's acidic. And then as you start to add some base, you're going to see it very slowly start to turn pink. Okay? It'll be colorless, 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 and then it'll be pink. And that's telling you when you have gone from acidic to basic, and that tells you just how much acid there was and just how much base you had to use to get there. Okay? And what we're doing there is a neutralization reaction, right? So if we look at the reaction that's listed here, it's an acid plus a base makes a salt plus water. Neutralization reaction. So nothing new. Okay? That's what I want to really, really reiterate to you, is that this is not a new concept. We're just putting sort of a new name to it, but it's nothing new, right? So let's take a look at this particular question here. Okay, so a chemist titrates a solution of nitric acid, and she finds that 23.4 milliliters of 1.05 molar sodium hydroxide is required to neutralize 25 milliliters of acid. what is the molarity of the original nitric acid solution? This, my friends, is solution stoichiometry. Nothing new, okay? You did solution stoichiometry in the previous chapter, right? And that's all that this is. So recognize, so we talked about this last time, is that when you see that capital M, that tells you that's going to be a conversion factor, okay? So let's tackle this just like we would any other solution stoichiometry problem, okay? We want to know what is the molarity of the nitric acid, right? So in order to get the molarity, I need moles and liters, right? I've already got the volume, tells me that I've got 25 milliliters of acid. So I need to find moles of acid. Okay, so let's start with our what we have the most information about, and that is the, kind of strangely done there, 23.4 milliliters of 1.05 molar sodium hydroxide. Sorry about the pause there, but realize that my worked out notes are incorrect. So I'm going to be calculating this as we go. All right, so the first thing, in order to use this conversion factor, I need liters. So I'm going to convert 23.4 milliliters to liters. Liters of NaOH. Okay, so now I'm going to use my molarity as a conversion factor to get moles of NaOH. Okay, and this is just like we did in the previous chapter. Okay, so my liters will cancel out, and that gives me moles of NaOH. Now I want to get to moles of nitric acid, so I'm going to use a mole ratio. That should be an H. Okay, so let's find out what that number is. 0.234 times 1.05. So we get 0.02457, tracking at the third sig fig, moles of HNO3. And then we, in order to get molarity, we're going to divide by the volume that we're given in liters. So we should find that the molarity is 0.9983 molar nitric acid. Okay, but I want to reiterate, and I'll say it until I'm blue in the face. Titrations are just solution stoichiometry. Doesn't mean this word neutralize doesn't really mean anything. The word titrate really doesn't mean anything other than it tells you that you're going to do solution stoichiometry. Okay, I want you to treat this just like you would any problem from the solutions chapter. Okay. All right, so let's do this one, and I do have the correct information for this one. All right, so what volume of 0.1 molar hydrochloric acid is needed to neutralize 25 milliliters of barium hydroxide solution? Okay, so first thing that you're going to need, and I've given it to you ahead of time, but you need an equation. Must have an equation. Okay, if you don't have an equation, you don't know what the mole ratio is, and you cannot solve this problem. Okay, so if you're not given one, you need to write one. And at this stage in the semester, I hope you are all confident in your abilities to do that. Okay, so we're going to treat this just like any other solution stoichiometry problem, right? Recognizing that we've got capital M there, and a capital M there. There's going to be conversion factors. Okay, so I'm going to start with the 25 milliliters of barium hydroxide solution, and I'm going to find the hydrochloric acid. Okay, so first thing I need is liters. So 25 milliliters into liters, 0.0250 liters. Right. Liters of barium hydroxide. And I'm going to use the molarity as a conversion factor. So 0.1 moles of barium hydroxide. My small handwriting skills are improving. So my liters will cancel out, and now I have moles of barium hydroxide. So if I stopped here, that's what I'd have. But I want to get to the moles of hydrochloric acid. Okay, so I'm going to use my mole ratio, and this is a perfect example of a type of problem that will never work if you use the dilution equation, but will always work this way. So that's why I want you to do it this way. Okay, so now I have moles of hydrochloric acid, and the question wants volume. So I'm going to use my other molarity as a conversion factor. So we can say liters over 0.1 moles of HCl. Right? And in the end, we find that we get an answer of 0.0500 liters, which equals 50.0 milliliters. Okay. But again, I can't say it enough, this is solution stoichiometry. Just because it's acids and bases does not change that at all. Okay, solution stoichiometry, you learned how to do that in the previous chapter. We're just slapping a new name on it, but it's still just solution stoichiometry. Every problem dealing with titrations, right? So your clues, right? Let's talk about clues. The word neutralize tells you that it's going to be a titration question. The word titrate will tell you that it's a titration question. Okay, but in the end, all you're doing is solution stoichiometry, nothing new. All right, here we go. It takes 50 milliliters of 0.2 molar sodium hydroxide to titrate, there's that word, 50 milliliters of sulfuric acid solution. What is the concentration of the sulfuric acid? Now, what did I tell you that you need? Very first thing, you need a reaction equation. Okay, so let's go ahead and write a reaction equation for this scenario. And we have H2SO4, sulfuric acid. These types of questions will challenge your nomenclature skills, friends. And I'm balancing it ahead of time because I already have this written out, but okay, but you have to have this in order to do these problems. Okay, you cannot go through this without it because you need the mole ratio. Okay, so let's take a look. We have molarity and we have a volume. So let's start with our conversion to liters. So we have 50 milliliters, divide by 1,000, 0.0500 liters, right? So I'm going to use my molarity as conversion. Liters of sodium hydroxide, 0.2 moles of sodium hydroxide per liter. So now I have moles of sodium hydroxide, and I want moles of sulfuric acid, so I need a mole ratio, and it's a 1 to 2. 1 mole of sulfuric to 2 moles of NaOH. Again, an example that will not work with the dilution equation. Right? So that ends up giving us 0.00500 moles of sulfuric acid, right? But the question says, what is the concentration, right? So concentration is moles over liters, right? Well, guess what? I've got 50 milliliters of sulfuric acid, okay? So now that I have moles of sulfuric acid, all I have to do is divide by that in liters. Gives us 0.100 molar sulfuric acid. Okay, but again, solution stoichiometry, folks. That's all we're doing here. All right, so the pH of a 0.25 molar sodium hydroxide solution is tested with a piece of litmus paper. What color will the litmus paper be? Now we can look at this a couple of different ways, and ignore the fact that the picture shows a blue strip because it kind of gives it away. But let's think about, how do we piece this together if we didn't have this image? Okay, so what do we have here? We have something that is an OH, right? So that means this guy is probably a base, right? So if I know the concentration of NaOH, I also know the concentration of OH minus, right? So if I wanted to, and let's go ahead and do that, I can calculate the pH of this. So I didn't work this out ahead of time, but because I just decided right now to do it. So the pOH is 0.6. Uh, 602. I'm being careful with my sig figs. And then my pH is 14 minus 0.602. Which means that my pH is 13.4 or 39. Right? Definitely more than 7. So basic. Right? And then blue for basic. Right? So there were several different ways that we could look at this problem right off the bat. I didn't have to calculate that pH. I could just recognize that NaOH is a base. Okay? And know that I'm going to end up with a basic solution. Right? A few drops of phenolphthalein were added to a beaker containing H2SO4. That's an acid, folks. Recognize it starts with an H, so sulfuric acid. What color will the solution be? Now, phenolphthalein indicator is colorless when it's with acid and pink when it's with base. So if I've put it in a solution of acid, it's going to be colorless.